Hey guys, this is Mr. Lowry. On day 3 of this week, we talked about 3 new properties of exponents. Last time on day 1, we talked about the product property, the power property, and the power of a product property. Today we're talking about this one, the quotient property, the zero exponent property, and the negative exponent property. Okay, so I'm going to give you some reasoning about the 3 of them, where they come from, and then some example problems. Okay, let's take a look at the quotient property for a second. Now, the word quotient is one of those key operation words, and quotient means we're dividing. So product means multiply, sum means add, difference means subtract, quotient means divide. So we're talking about division here, and we're talking about dividing things that have exponents. So let's take a look really quick at something like this. Let's say you had x to the 5th divided by x to the 3rd. Now we can find out what this is. We can simplify this by expanding, right? Just that kind of our regular thing that we do. So if I expanded this out, multiply all these 5x's on top, okay, and then you divide that by x times x times x. So 5x's on top, 3 on the bottom. Now we know that when we have a number over itself, we can simplify that to 1. For example, if I have 3 over 3, we know that's 1. Or 4 over 4, that's equal to 1. Or 10 over 10, right, that's all equal to 1. So anytime I see an x over x, I can simplify that to 1. And usually what we do is we just cross that out. Because if there's other stuff there, then x over x is just 1. So cross this out, cross this out, cross this out, right? Anytime we see a common factor in x over x, we're going to turn that into a 1. So what we have left here is we have an x times an x. Okay, now on the bottom, it kind of looks like all the x's canceled, but if all the x's cancel, we end up with like a 1 as like a placeholder there. Because remember, when we cancel, we're getting 1s here. And that is equal to x squared, right? X times x is x squared, and then divide by 1, that's the same as just x squared. Okay, so that's how you would solve this by expansion. Now, we don't want to expand every single time. What we want to do is we want to find some shortcuts, some rules, or some properties that allow us to do problems like this a little bit shorter. So we expand to see what's happening, to look for patterns. And then once we find those patterns, we say, okay, that's a property, that's a rule, and then we use those rules instead. So let's look at what's going on here. If you think about 5 and 3 and 2 and how they're related, 5 minus 3 is equal to 2. So if you have 5 x's and you cancel 3 of them, take away 3, you're left with 2, right? 5 take away 3 is 2, or 5 minus 3 is 2. So in a situation like this, where you're dividing 2 things that have the same base but different exponents, what you can do as kind of a shortcut is you can just subtract the exponents, right? X and x, so you're going to have x's. You just got to figure out what 5 minus 3 is, and that becomes your exponent. Okay, that's the quotient property. So just writing it generically so that you have this in your notebook, the quotient property looks something like this. We don't use specific numbers, we use generic numbers, letters to represent. So what this looks like is anytime you have 2 exponential expressions being divided and the bases are the same, what you're going to do is subtract the exponent. So this x represents any number or letter. This x represents whatever that is, the same thing, right? So the same number or letter as what's above. What you're going to do in this situation is you're going to have one of that base and you're going to subtract the exponents. So this is like a formula kind of that's saying when you have a situation like this, this is what you need to do, subtract the exponents. Okay, let's look at a couple examples of that, and then we'll talk about the next property. Okay, so some examples. Let's say you had y to the 1,000 over y to the 998. Well, those seem like pretty big exponents, and if you expanded this, you'd be here all day, right? Y times y times y times y times y times y. So you don't want to expand it, you want to use the shortcut. See if I can get a little closer here so you can see what I'm writing. Those exponents are kind of small. So this is 1,000, this is 998. So I'm basically just going to subtract the exponents. 1,000 minus 998 is 2, so I just have y squared. Okay. Now sometimes what you'll see is you'll see something with other numbers in it, and that's okay. So let me give you an example of that. Let's say you had 4x to the 7th over 8x to the 3rd. And you see those other numbers. Well, these other numbers here, these just act like a regular fraction. 4 over 8, we just want to simplify. What goes into both of them? Well, 4 goes into both of them. 4 goes into 4 once, and 4 goes into 8 twice. So this is just 1 over 2. Now keep that fraction bar there, because we are going to keep doing the product property here. Excuse me, the quotient property. So now that I've done the number part, now let's look at the variables and their powers. So x to the 7th over x to the 3rd, I'm going to subtract those exponents. 7 minus 3 is 4. So I have 1 times x to the 4th over 2. And I don't really need to write that 1 anymore. That's just multiplying the x to the 4th. So how I would write this is x to the 4th power over 2. So that if there's coefficients in front, numbers in front, you're going to simplify them like normal. Now the exponents are different, right? The exponents we're going to subtract. So that's kind of a different story. Use the quotient rule here, subtract the exponents. But for the coefficients, the numbers that are in front of the variables, just simplify them like a regular fraction. Okay? All right. Let's talk about the zero exponent property for a second. Okay? I think what I'll do here is I'll give you the property first and then explain where it comes from. Okay, so the zero exponent property looks something like this. Anything to the 0 power is equal to 1. Okay? That's kind of confusing because you know if you multiply by 0, you get 0. But this is not multiplying by 0. Let me show you what this means and why it's a 1. Okay? I'm going to give you I'm going to give you an expression, and we're going to simplify it 2 different ways. Okay? So let's go back to powers here, and let's take an x to the 3 over x to the 3. And let's start by simplifying this with expansion, right? That's kind of like, it's the longer way to go, but it's also the safer way to go. And it's the way we find out all of our properties. So on the top, x times x times x, right? On the bottom, x times x times x. And we start canceling, right? X over x is 1, and x over x is 1, and x over x is 1. And you're like, wait, everything's gone. And so you think, well, what's left? Well, what's left is a 1, right? So if you think about what we talked about a little bit earlier, 3 over 3 is 1, 4 over 4 is 1, 10 over 10 is 1. And so you have what these are, they're called multiplicative inverses. So you have a 3 divided by 3, a 4 divided by 4, right? You just end up getting 1. Okay, so over here, when you cancel everything out, you're left with what's called the multiplicative identity. There's a 1 there, right? So that's the answer to this problem. Now let's look at the problem from a different perspective. So same problem, but let's use the quotient rule that we just talked about up here, right? The quotient rule, the shortcut, says subtract the exponents. Okay, so let's do that. If I got 2 expressions with the same base, right, x and x, and I subtract the exponents, I'm going to get x to the whatever 3 minus 3 is, and that's x to the 0. Kind of weird, right? Since these are both the same expression, and we're simplifying them, we know that the final answer is the same. Even if they look different, they must be equivalent, right? So x to the 0 is equal to 1. Now think about that for a second. What does the 0 mean? It's basically like all the x's canceled and there's none left. But if all the x's canceled, you don't have 0, you have a 1 left over, right? Remember, x over x is 1, x over x is 1, x over x is 1. So when all the x's cancel and you have 0 left, there's still a 1 there, that multiplicative identity. Okay, so anything to the 0 power is 1. Sometimes you'll see this property written a little bit differently, like you might see it written with a different variable, but the idea is the same. Anything raised to the 1 power, anything raised to the 0 power is 1. Okay, now we need to do some example problems just so we don't get tripped up, but let's take a look at a few. Okay, so let's do 3 this time. Let's do 1 million to the 0 power. Come back and look at that in a second. And then let's do 3x to the 0 power. And then we'll also look at something kind of similar. And let's do one more, actually. Okay. So what I told you a minute ago is anything raised to the 0 power is 1. So 1 million raised to the 0 power is 1. Okay? Now, just because anything to the 0 power is 1 doesn't mean that when you see an exponent of 0 that your answer is 1, because it kind of depends on what's being raised to the 0 power. So take a look at 2, for example. When you look at 2, and you're trying to think what's being raised to the 0 power, it's only the x, not the 3. This is 3 times x to the 0, and if you want to add an exponent to that 3, you could say it's 3 to the 1 power. Okay, so I got 3 to the 1 times x to the 0. Only this piece is being raised to the 0 power, so just that piece is 1. So I have a regular 3 multiplying a 1, and that's going to give me a 3. Okay. So what I said was true. Anything being raised to the 0 power is 1, but in this case, 3 is not being raised to the 0 power. So that part is 1. X to the 0 power is 1. Then when we multiply it by 3, we get 3. Okay, now this one, number 3, is a little bit different because all of this stuff is now being raised to the 3 power. Excuse me, to the 0 power. So this thing, anything raised to the 0 power is equal to 1. You could also think of it using our power of a product, right? So we have this product, 3 times x, being raised to a power. That means both the 3 and the x get a 0. And 3 to the 0 is 1, and x to the 0 is 1. So this is 1 times 1, which is still 1. Okay, so any way you slice it, it's going to be 1. Okay, this one's kind of tricky because it's harder to see the order of operations, but remember that when you're looking at something like this, only the 12 is being raised to that power. The negative is not. So what this looks like is basically -1 times 12 to the 0. Order of operations says take the 12 to the 0 first, and then when you take that answer, you're going to make it negative. Okay? So 12 to the 0, that is 1. But we're multiplying that by -1, and so our final answer here is -1. Now we could change that problem a little bit if we did this, right? If we put the negative on the inside of the parentheses, then we're saying, okay, take this whole thing to the power of 0, and this guy would be +1, but not this guy. Those are different problems. Okay, so that is the 0 exponent property. Okay, one more. Let's look at the negative exponent property. Okay, and again, we're going to look at 2 different ways to simplify the same expression. So let me do x to the, let's do 3 over x to the 7th. Okay, and we're going to look at it twice. The first way we're going to do it is by expansion, the old standby. Okay, it's pretty reliable. You can pretty much figure out what you're going to have using expansion, but it also takes a long time, and when the problems get really complex, it's not the way you want to go. 1, 2, 3, 4, 5, 6, 7. Okay, so we wrote it out, we expanded it, now let's cancel. So gone, gone, gone. Well, what's left? Well, we got 4 x's, right? But those are like on the bottom of this fraction. So when everything cancels on the top, I still have a 1 there. Remember that 1 is our multiplicative identity. When everything, so this is a 1, this is a 1, this is a 1. If there's nothing else there, then it's got to be a 1. On the bottom, we have x times x times x times x, and that's x to the 4th power. Okay, so that's one way to look at it. Now let's look at it using the quotient rule. Quotient rule says if you're dividing and the bases are the same, subtract the exponents. So be careful here, because this isn't 4. If you do it in the right order, it's x to the -4, right? 3 minus 7 is -4. So again, let me zoom out a little bit. These things have to be equivalent because they came from the same problem. We just looked at it from two different perspectives, two different methods. These must be the same thing. Let's think about what that negative 4 means. Okay, the only way I'm going to get a negative number by subtracting is if the bottom number is bigger, right? So if the bottom number is bigger, I get a negative. What this negative means is you have 4 x's, but they're on the bottom. They're down here. So negative 4 indicates the 4 that you have left over are in the denominator, not in the numerator. Okay, so these things are equivalent. So the negative exponent property looks something like this. X to the negative a equals 1 over x to the a. So if I have something raised to a negative power, that's the same thing as a fraction with that positive power on the bottom. So negative a means a bunch of x's canceled, and I have a x's left on the bottom. Okay. Sometimes you might see this property written out with different letters. Sometimes you'll see it like a to the negative n equals 1 over a to the n. It doesn't really matter. The idea is the same. When you have that negative exponent, what you want to do is you want to move that whole quantity down to the bottom of a fraction and then make that, that exponent positive. Okay. Let's look at a couple examples, and I'll give you a really silly analogy that is it's kind of weird, but it'll help you remember. Okay. So example number 1. What we want to do is we want to rewrite, actually let's use a number on this one. We want to rewrite this expression so that it doesn't have any negative exponents. We want to write an equivalent expression. Okay? So think of this 2 and this exponent of 3. Think of this exponent as like a thought bubble. Right? It's kind of like up above the 2. So it's like this 2 almost is like thinking about a negative 3. So the analogy is kind of silly, but imagine this 2 is thinking of a negative number, right? That's kind of like it's thinking negatively. It has a bad attitude. It's got negative thoughts here. It's being negative. And so what we do, again, this is kind of silly. We're going to punish this 2 by sending him downstairs to the basement. Okay, so we put a line here for our fraction, and we move that 2 down to the basement until his attitude improves, until his thoughts become positive. So 2 to the negative 3 becomes 2 to the positive 3 when it's downstairs. Right? His negative thoughts turn to positive thoughts. And of course on top we have to have a 1 because we have to have like a placeholder there. Okay? So I call that the bad parent analogy, because if you're having a bad attitude, it's probably not going to improve matters much to get punished, but it helps me remember. So we punish that 2 that's thinking of negative thoughts downstairs. We banish him to the basement, and we get this fraction. Okay, let's look at a couple other examples here. Okay, so let's do. Also, sorry, one more thing, really quick. We could finish evaluating this because 2 is a number. So just as a practice, what I want you to do here is type in this number into your calculator, just like that, 2 to the power of negative 3. And then I want you to type in 1 divided by 2 to the 3. And in either case, you should get 1 over 8. Okay, since we're using numbers here, you could actually verify this, use your calculator to verify that these are actually the same thing. Okay. All right, example 2. What if you had 5 to the negative 2? So 5 is thinking bad thoughts, negative thoughts, and so we send 5 down to the basement until those thoughts improve, until that attitude improves. Okay. Now if we wanted to, we can change this into an actual number because we can do 5 squared. Okay, a couple more. Let's do x to the negative 10. Okay, it doesn't matter if it's a variable. It's got a negative exponent. Again, that's kind of like a negative thought bubble, right? Thinking negatively. So we send it downstairs until its attitude improves. Okay. Let's look at a scenario where we have a little bit of an extra piece. Okay, so what if I had 3x to the negative 2? Okay, again, it's really, really important to understand which piece is being raised to the power and which piece isn't. And because of order of operations, this is being raised to the negative 2, and then it gets multiplied by 3. So this 3 is not being raised to the power of negative 2. It's actually being raised to the power of 1. So when we send, it's almost like these are siblings, right? You have a 3 and you have an x. And the 3 is thinking about a 1, positive, and the x is thinking about a negative 2. So the 3 is fine. The 3 doesn't change. 3 stays on top. X is the one that gets sent to the bottom until its thoughts improve. Okay, so the 3 stays on top in this case. Now let's look at one more scenario that's similar, but we're going to add some parentheses to change up the order of operations. Okay, let's do 3x, and we'll put that in parentheses, and then we'll take that to the negative 2. Okay, now this changes things because now the 3 and the x are both being taken to the negative 2 power. So think of this now as just one person, or maybe two people, but they're both going to get sent to the basement. So we send the 3x down to the basement, that pair, until their attitude improves. Okay, now from here, we can use another property of exponents, the power of a product. So we know that this too applies to both of these pieces, both of the factors in this product. So we have 1 over 3 squared and x squared. And since 3 squared is 9, our final answer is 1 over 9x squared. Okay, so that's the negative exponent property. Now, those properties are a little bit confusing, and I want to show you one more idea that will kind of help you understand those properties. Okay, and I'm going to make like a table basically. So check this out. If I had 2 to the 4th, we know that's 2 times 2 times 2 times 2, right, with expansion. 2 times 2 is 4, and this other 2 times 2 is also 4, so we have a 4 times a 4, which is a 16. Okay, let's do 2 to the 3rd. So 2 to the 3rd is 2 times 2 times 2. 2 times 2 is 4, and 4 times 2 is 8. Okay, let's do 2 to the 2. We're just going to keep this pattern going, and then we'll talk about why the 0 exponent property and the negative exponent property actually make sense. So 2 squared is 2 times 2, right, which is 4. Okay, and 2 to the 1 power, that's just one copy of 2, so that's just 2. So look at the pattern here. We talked about exponential growth functions, and it looks kind of similar. 16, 8, 4. The pattern is we're having, right? As we go down a power, we have to half what we had before, because it's like if there's one less factor of 2. So looking at this pattern here, this is divide by 2, divide by 2, divide by 2, right? Let's keep going. Let's see what happens. So if we have 2 to the 0, a lot of times people are like, oh, that's got to be 0, right? Because 2 times 0 is 0. But this is not 2 times 0. What the idea is that we have to continue this pattern. So what's 2 divided by 2 if we keep this pattern going? 2 divided by 2 is 1, right? So it's like all the 2's canceled out, and when everything cancels, you still are left over with the 1. But you can see that in a different way looking at this pattern. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. It would be weird if there was a 0 here. Let's keep the pattern going. Okay, so now we have 2 to the negative 1 power. Okay, kind of hard to figure out what's going on here, but let's figure out what's going on the right-hand side. Okay, we're going to keep this pattern going by dividing by 2. So 16 divided by 2 is 8, 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1. What's 1 divided by 2? 1 divided by 2 is 1 over 2, right? So see how that negative exponent is really a positive one when you put it in the fraction. Negative exponents represent fractions. They represent multiplication or factors that are on the bottom of the denominator. Okay? Let's keep going. 2 to the negative 2. Okay? Now again, the repeated multiplication is kind of hard to figure out what's going on. I'll write that in just a second. But let's see what's going on here, okay? So back over here, I'm kind of continuing. I have to take 1/2 and divide it by 2, right? So 16 divided by 2 is 8. 8 divided by 2 is 4, excuse me. 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is a half. What's a half divided by 2? 1 half divided by 2 is the same as 1 half times the reciprocal, which is a fourth. So 2 to the negative 2 is 1 over 4. But isn't that the same as 1 over 2 times 2? So again, this negative 2 represents multiplication by the factors of 2 on the bottom. Okay, let's do one more. 2 to the negative 3. So once again, I have to divide 1/4 by 2. If I'm going to continue this pattern, 1/4 divided by 2 is the same as 1/4 times 1 over 2, which is 1/8. So this is equal to 1/8. But if you think about it, that's 1 over 2 times 2 times 2, right? So check it out. 2 to the third is 8. 2 to the negative 3 is 1 over 8. 2 to the 2 is 4. 2 to the negative 2 is 1 over 4. 2 to the 1 is 2. 2 to the negative 1 is 1 over 2. See how that works? So all these negative exponents represent fractions. It's 3 copies of 2 on the bottom. Negative exponent, the negative means they're on the bottom. Okay. Also, we see that 2 to the 0 power is equal to 1, not 0. So that's just another way to look at what's going on here, right? We talked about these properties. The negative exponent property says if you have a negative exponent, push it downstairs and make the exponent positive. Because, going back to this idea, negative exponents represent fractions. The 2's, the repeated 2's, are on the bottom, and there's 2 of them. Okay? Going back to the 0 exponent property, anything raised to the 0 power is 1 because it's like everything canceled. We divided everything out, but that means there's still a 1 there. When all the things cancel by multiplication and division, we're still left with a 1. Okay? So there's some examples for you. That should help you with your worksheet, and have a good spring break, guys.